So I asked you to pick up this big copy of the reference table. If you've noticed, this reference table is legit the exact same reference table that you will find on page 10 of your actual reference table. I just like the larger copy to get a little more comfortable using it. So we're gonna stick with using this page 10 of our reference table, the large copy of it. And we're actually gonna do some color coding of it today. I really think that coloring this reference table makes it a little bit easier to use. So you may have noticed I put some colored pencils around the room. If you have your own or would like to use a highlighter instead of colored pencils, you can do that. The colors aren't going to matter. So that's why there's just a few buckets of pencils to share amongst everybody. So we're going to do this strategically. So if you guys just hold off coloring each layer until I've asked you to, that'll work out good for me. So first of all, you might notice that this reference table is broken up into 3 sections. We have the top, which is like a picture. We have the middle graph and the bottom graph. So we're going to start with the picture. Does that picture look familiar at all? Where did we see a picture similar to that? Yep. See a few of you pointing to right here. Now the picture is not exactly the same. They're out there already, the colored pencils. Pictures aren't exactly the same, but what I want to point out is that this picture on your reference table is equivalent to that much of the picture I gave you on the front page of your packet. So they didn't give you the whole Earth. They basically just gave you a slice or a quarter of the Earth as a picture on your reference table. So again, there is that. So you can see at the top, this is where you would be walking. So if you did want to add a picture of yourself up there, that's where you would be walking. And then you can see that you would dig down through the layers and get to the section labeled the center of the Earth. The best part about this reference table is all those words that we defined yesterday: lithosphere, crust, asthenosphere, stiffer mantle, outer core, inner core. They literally label them: inner core, outer core, stiffer mantle, asthenosphere, crust, rigid mantle, and lithosphere. Everything is labeled. So basically everything we did yesterday, nothing needs to be memorized. It's all right here. I did want to get you a little familiar with them before I just threw this reference table at you. This reference table has a lot going on. So that is one reason I like to color code it and color code it slowly. So what I'd like you to do is either grabbing your own or grabbing a cup or sharing a cup of colors with the people around you. Just grab one colored pencil. We're going to actually start from the inside out here. So we're going to go ahead and we're going to color the inner core. Now, when I say color, please actually more like shade, because I need you to be able to see through your coloring. So don't practice coloring as hard as possible. Just shade it lightly. So we're going to shade that section. And what you'll notice is you've colored over the words iron and nickel. Logan, can you grab one and follow along with us? You're supposed to pick up the large copy. So, and while you're over there, can you turn off all the lights? Thanks. So you colored over the words iron and nickel. What do you think that's trying to tell you about the inner core? It's what it's made out of. So the inner core, they flat out tell you it's made out of iron and nickel. Now we're going to go over here and color this dotted section here where it says 12.8 to 13.1. What are those numbers? Can you figure it out from the reference table?
Density.
So see how density is listed over here, right up at the top? All of these numbers are the densities for the different layers. So we've now colored the density for the inner core, the same color as we colored the actual picture of the inner core. You'll see that they labeled the Earth's center right here. So this part is the dead smack center of the Earth. Just like it would have been here, it's this spot right here. That's the dead smack center of the Earth. That's the picture. So that tells you what it's made out of and its density. If we look down at these graphs, this graph here is telling you the pressure of the inner core and the temperature of the inner core. And then the x-axis for both graphs is the depth for each layer. Now, I want to point out that where the inner core and the outer core meet, there's a line there. That line switches to a dotted line. Do you see how that dotted line does not line up with the 5,000 mark? Here's where I need you to practice your good coloring skills. We're going to color, but you have to stay in the lines. Do not go over the dotted line. So we're going to color the whole graph section of the inner core. We're going to color it blue, or well, whatever color you're using. I'm sorry. So just stay, do not go over the dotted line is what I'm trying to say. Do not go over to the 5,000 mark. You can, yeah. Thank you. So I know mine isn't showing up super great on the screen, but again, don't color so dark that you can't see underneath it. And as much fun as coloring is, can you make sure you're almost done with the inner core? I know coloring is fun, but we do have things to learn. Yeah, I'm not teaching you to color right now, so we're teaching inner core. So let's start with the depth. The depth is the x-axis. There are two graphs here, a temperature and a pressure graph. They both use the same x-axis. So because there's nothing listed up here, you're going to just use these numbers down here. So the depth tells you like how deep you'd have to get, or like if you were to dig a hole, how deep you'd have to dig that hole till you reach, so I'm digging until I reach the top of the inner core. So let's actually look at this depth chart and figure out, well, how deep is the top of the inner core? So that actually leads me to a good point. Is it 5,000? No, you can see that that dotted line is a smidgen, just a tiny bit to the right of the 5,000. Does that mean it's deeper or shallower than 5,000? Little bit deeper. How much you want to estimate that to be? I would keep in mind that like here about would be the 500 mark. I do think 200 might be a little bit over. Honestly, I think even 100 might be a little bit over officially, but let's stick with a 100. It's close enough. We don't need to get into absolute details like that. 100s are fine. What I'm going to do is, because I don't have a lot of room to write there, maybe you can write smaller. I'm just going to put an arrow pointing to that dotted line, and I'm going to label it 5,100. If you called it 5,075, they'll give you credit. If you called it 5,200, they'd still give you credit. Just don't call it 5,000. Don't call it 5,500 either. It's nowhere near the 5,500. How about the center of the earth? So here's the center of the earth. What would you call that depth?
400, 300, 300.
Is it 6,000? Do you think that that's a whole half a box? Would that be 6,500? No, I agree with that as well. Like Carson was struggling with, is it 6,300, 6,400? Either one is good. I'm going to go with 6,300. I'm also, since I have room to label, I'm going to bring down that label that said Earth's center. By the way, these are in kilometers, in case you didn't notice that. Kilometers just a little bit less than a mile. So it's pretty freaking deep. A lot of miles. So that's the depth. But what about the graph for the temperature? So one question that they're going to ask you, well, is what's the temperature at the center of the earth? So this is just hot. I will agree with that statement. It's hot. This is just a normal graph. You guys don't have to write this, but I'm just going to make up any old graph over here. if you study, so this is going to be the hours, and this is going to be your grade, and this is 100% made up. So let's say this is an hour, 0 and 1 hour. Halfway would be a half an hour. And again, this is made up, 0 and 100, and this is what the graph looks like. According to this graph, if you studied for a half an hour, about what would your grade be? How'd you figure that out? Walk me through. You go to the half an hour, right? Then what'd you do, Logan? You go up till when? Until you get to the line. Then we go over to the left, and according to mine, it's a little bit less, it looks like, than halfway. I mean, this is a tough test. So maybe a 45. Those of you who had said 50, close enough. You guys know how to read graphs. Again, this is made up. I do not think anybody who studies for a half an hour will get a 45 on any of my tests, even the Regents. But you know how to read a graph. You start at the x-axis, you go up till you hit the line, you go over. Would you be able to read this the other way? Like, how long would you have to study to get a 75? So 75's around here. How do I figure out your grade, how long you'd have to study? So do it in reverse. You go over, so you hit the line, go down. So you'd be just short of an hour. You guys know how to read a graph? Let's read this graph. How hot is it at the center of the earth? No. So again, we go to the center of the earth. We go up until when? Till we hit the line. Now, what line do we need? We want the actual temperature line. That is, the black line is the actual interior temperature line. Now, you could go over here to estimate, but as long as we're here, like we can pretend that there are labels over here. Is it at 6,000?
No.
Is it 7,000? Is it halfway? Little higher, little lower? Little higher. So what would you estimate that to be?
67.
66, 67. So 6,600. I'm not even going to label it because yeah, why not? 6,600. If you said 6,700, they would not care. They might mark you off if you said 6,500 because you can tell it's a little bit higher than that. Okay, not so bad, right? Then there's the pressure graph. So the pressure again uses the same x-axis. But now our y-axis is listed as 1, 2, 3, 4 million atmospheres. For the record, and maybe you want to put this at the surface. So where we're standing right now, or I guess technically where we're sitting, there is 1 atmosphere of pressure on us right now. An atmosphere, by the way, is how they measure air pressure. There's 1 atmosphere of pressure on us because there's the equivalent of, well, 1 of our atmospheres on us. So there's 1 atmosphere on us right now. This 1 is not 1, it's 1 million. This 4 is not 4 times the pressure we feel right now. 4 million times the pressure we feel right now. So when you guys said it was hot down here for temperature, it's really a lot more pressure. We're talking 4 million times the pressure we feel right now.
Is that when you go down in a pool and your ears get like...
So this is the equivalent of going down in a pool and your ears feel weird. Why do your ears feel weird at the bottom of the pool? All that water is putting pressure on your eardrums. So now it's not water putting pressure on your eardrums. It's all this layer of the earth. So there's a lot of pressure doing the same idea. It's pushing down and making a lot of pressure, just like the water is pushing down on you when you go to the bottom of the pool. So it's the same idea. The farther you can see, if we start at the top of the earth, so at 0 kilometers, we have a very low pressure. The deeper we go, we get a higher pressure. That makes sense because there's more stuff pushing down on you. But let's do the actual estimating this. How much pressure exactly is at the center of the earth?
3,750,000.
So same deal. I can use this side of the chart just as easily. Is it at 3? Is it at 4? Would you say it's halfway, 3.5? Tiny, teeny, tiny bit more. I think they might even let you get away with 3,000 or 3.5 million. But I do agree. I think it's a little bit higher, maybe 3.6 million atmospheres. So you guys can read, figure out the temperature, figure out the pressure anywhere on this graph. One more thing. I kind of skipped over that dotted line. What's the dotted line labeled? Melting point. You guys know what melting point is? What happens when we reach the melting point of water? Like, so it's depending on, it doesn't boil. Melting point. So if I had an ice cube and or if I had a cup of water and I got cold enough that it hit the melting point, what's it going to do?
Transform.
If it's getting colder, it's going to freeze. But what if I go and it's hotter than the melting point? What's going to happen to this? It's going to, not water vapor because it's a cup of water.
More water.
Or so it was ice. Okay, maybe I think I messed this up.
It's gonna turn into a liquid.
It'll turn into a liquid. So if I have a cup of water,
Oh.
in this room right now, is the temperature warmer or colder than the melting point?
Colder.
In this room right now?
Oh, it's warmer.
What's the melting point of water?
35 degrees.
32 degrees Fahrenheit.
32.
Is it warmer or colder than 32 in here? Warmer. So is this water or ice? Water. So it's melting. What if out in the freezer in the back?
Frozen.
It's frozen. Why?
It's cold.
Because the freezer is colder than the melting point. So it's still going to stay frozen. Here, let's take a look at the inner core. The inner core, the melting point is warmer than the interior temperature. So does that mean that the inner core is a solid or a liquid? Think this one through. Think it through for a moment.
Solid.
It is going to be a solid. So here it's saying the actual temperature is colder than the melting point, just like a freezer. A freezer is colder than the melting point of water. So it's going to be solid in the freezer. Yeah.
How do we know what the melting?
They tell you because it's the dotted line.
So like, how do people figure that out?
How do people figure it out? Science. Let me show you the title of this reference table. It's called the inferred property of Earth's interior.
No, 100%.
Right. So inferred. What did we learn about inferred at the beginning of the school year?
Based on observation.
Guess based on observations. So these are literally almost everything here is a guess based on observation. You know the phrase barely scratched the surface?
Yeah.
Have you ever heard that? What does it mean?
It's like we're barely there.
We're barely there. Like if we say you have barely scratched the surface of the earth, that is literally what we have done as a human race in general. Humans have only dug down just into the rigid mantle. So if this is the rigid mantle here, this white line, we have literally only ever been there. So we don't know for sure any of this stuff, but we use our observations. Scientists know that earthquake waves travel through different materials and temperatures differently. So kind of like if you were to throw a rock into a pool versus throwing a rock into a bowl of Jell-O or a bowl of pudding, will the waves behave the same way in both?
No.
They will still be waves, but they're going to be all messed up in that bowl of pudding. Those waves are going to be different looking than in a bowl of water. Same if we threw a rock into a frozen solid bowl of water, so ice, if the wave is going to behave differently. So scientists You don't have to know, by the way. Scientists know how those waves travel, and they're able to study these shock waves as they go through Earth and make a guess based on their observation of what it's going through. So scientists know what waves look like if they go through iron or nickel or solids or liquids. They also can do experiments to figure out, well, will iron and nickel be a solid or a liquid at this temperature and this pressure? So they can then assume what the temperatures and pressures are. So back to your question, Carson, you said, how do we know? You know because you read it off the reference table. How do they know? They've done experiments.
Then like, how do we know it's made out of iron and nickel?
Because of, again, the way the wave will travel. So they know they can test how high the waves go, their amplitude, their frequency, and compare it to how those waves travel through those materials in real life. And so they're not lying, but they could be mistaken. There are definitely things that could cause it to go differently.
What if my kid calls me stupid in 20 years because of this?
So it's definitely a possibility. I mean, and that's where you have to educate, like, were they stupid when they thought the sun revolved around the earth? No, they weren't stupid. They just used the information they had.
Weren't educated.
It's not that they weren't educated. They were educated on what they had, but they just didn't have any more of the information. But back to this, because we do have to get through this. So again, how do we know that this is a solid layer?
Because the melting point is higher than the temperature of that.
Okay, so it's a solid because the melting point, let's actually put a little note there. I'm gonna put just a note right around here. This is a solid because the actual temperature is colder than the melting point. That I have seen as a Regents question, by the way, a two-parter. They'll ask, is the inner core solid or liquid? And how do you know from the reference table? It is a solid because the actual temperature is colder than the melting point. Grab a different color. We're going to do the same thing for the outer core. Again, we're going to color its density. You'll notice it's less dense. Why is the outer core less dense? Oh, and while you're coloring, you're going to notice that it's made out of iron and nickel. It's not as compact. Well, how come? There's not as much pressure because there's not as much stuff on top of it. Again, make sure you're coloring carefully. We want to go over that 5,000 mark to the top of the inner core. And you're going to want to go over that 3,000 mark because the top of the outer core also doesn't line up perfectly. And again, if you're not almost done coloring, please speed it up. So we're just going to cover a couple of the same things. What is the depth of the top of the outer core? What is the depth at the top of the outer core? Do you see that it is just to the left? Sorry, don't know my right and my left. Do you see that the dotted line is just to the left of the 3,000 mark?
Good.
So the depth there is about 2,900 kilometers. Again, do not call it 3,000, but if you called it 2,950, they'd be fine with that. Now take a look at the temperature and the melting point of this section. The outer core, is it going to be a solid or a liquid?
Mostly.
Yes, mostly a liquid. I like how you said that. So again, I'm gonna bring an arrow to describe that this area is liquid. Again, how can I put in words that I know that the outer core is liquid?
Melting point is lower.
Yep, I go the other way and I talk about the actual temperature. So I am going to say the actual temp is hotter than the melting point. Grab a third color. We're going to do the same thing for the stiffer mantle. Now this time for the density, we're not going to color that whole dotted section. We're going to follow the line for the top of the stiffer mantle. So we're leaving a little bit of the top of that area blank. Again, if you're not done coloring, please speed it up just a moment, please. So I don't really have too much to talk about with this area. You can see again, are we back to a solid or a liquid here?
Solid.
Solid. The actual temperature is way colder than the melting point. I'm going to leave the label off because I already did both of those. And we're going to move on into the asthenosphere. So grab what would be your fourth color. Now here, I want to talk about the density. So there's no numbers listed here in this little section. But according to this, what is the density? It's still in a specific bracket. Nope, it's in this. So see how it's underneath this dotted line here? This is going to be that 3.4 to 5.6. It's the same as the one below it. So it's part of that mantle section. And again, with the colored pencil, we're going to color do not go up into that next layer, that really skinny white layer, because that is a different layer. So here again, it's really important you color in between the lines. In between both sets of dotted lines. What would you say the depth of this layer is? Where does it start? The top of this?
600.
100?
Oh, like 100.
Is it 0?
No.
It's a little bit to the right of the 0. I agree, that's 100. What about the bottom of this layer? Is it 1,000? Is it halfway? Is it 500? I'd say it's about 600 or 700. I agree. So I just labeled those two dotted lines. It starts at 100 and goes to about 600. Finally, we have to color the lithosphere. Yesterday, we took notes on the lithosphere and said it includes the crust and rigid mantle. Good news. You don't have to memorize that. Right here, they tell you, and I am going to color this section as well at the top, that the lithosphere is the crust and the rigid mantle. if you follow those lines, the crust is pointing to the solid black line. The rigid mantle is pointing to that skinny white section. And yes, we are going to attempt to color this section. This is where even our expert colorers might have some issues. But it is this very, 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 very thin layer. And this goes from 0 down to about 100. Now the densities, they list them up here. The densities are slightly different depending on where you're measuring. It says it has a density of 2.7 for the granitic continental crust and 3.0 for the basaltic oceanic crust. Mrs. Ritz. Yep. Olivia, they will need you in guidance when the bell rings. Real quick, does the word granitic and basaltic sound familiar? What do those sound like? Granite and basalt. Hopefully you're remembering. So you might have to flip back to what we learned last chapter. Granite is a coarse-grained igneous rock. Basalt is a fine-grained igneous rock. Does that make sense that basalt would, the oceanic crust would be made out of an extrusive rock, while the continental is made out of an intrusive igneous rock? It doesn't make sense. Where does an igneous rock that hits water, what's that? How fast is that going to cool? Really fast. If it's on the land, it's going to take a little bit longer. Also notice granite has a density of 2.7. Basalt has a density of 3. Remember, basalt is on the right side of the chart. It has a higher density and is mafic, while granite is on the left side of the chart, has a lower density and is felsic. So all that information can be gotten off of this reference table. So you have no actual homework tonight, but like I've been mentioning, I'm not going to be here tomorrow. Tomorrow, you are going to practice with this reference table a whole bunch. So if you guys could turn to page 3 of your packet, you're going to be doing tomorrow. And I did put this on the board for anyone who's not going to be here. Thursday, we're doing page 3, 4, and 5 of this packet. It is strictly questions about this reference table. So let's try and just do a few of them. My first one I want to do is question 5. Question 5 says, what is the temperature at a depth of 3,000? So yeah, temperature, it wants to know the temperature at a depth of 3,000. How do we go about doing that? Go to 3,000. Next, what's next? Go up. So we are following the solid 3,000 mark. Hit the black actual interior temperature. I would say it, but no, you're looking at the dotted line. So we want the solid 3,000 line. I think that hits right at 5,000 degrees. Can I ask you now to check out question I think you could probably do the rest of them. So that's asking you for those ones. Now let's flip over to page 4. I'm asking here, so still more of the exact same types of questions. Now I want to know the depth range. What do I mean by range?
From where to where?
From where to where it starts to where it ends. To be honest, I think it's easier to start at the inner core. What is the depth range for the inner core? So you can follow this down. It's my blue section. What's the range here? Yep, so it starts here at this dotted line, which we already labeled as 5,100, and it goes to the inner core, so 6,300. So that's 5,100 to 6,300. 300. One more that I want to do together. The next question asks how thick each section is. How do I figure out how thick the inner core is?
Yeah.
I subtract. I already know where it starts and where it ends. So now I just have to subtract those two numbers. So when you subtract 6,000, and of course you can use your calculator, that gives us 1,200 kilometers thick. I will warn you, it's hard, these numbers get a little wonky when you're talking about the really thin ones, but you can still handle it, I'm sure. So as it says over there on the board, you have no actual homework tonight. Thursday, literally the whole period, you are working on completing pages 3, 4, and 5. It's a hefty amount of work. You have 42 minutes to do it tomorrow, or is it just 40, whatever. You have 40-ish minutes to do that. If you don't finish it, it's homework. On Friday, I will also not be here. On Friday, what you will be doing is you are going to be learning about continental drift. My guess is you already know a tiny bit about continental drift. What do you get from its name? Continental drift. Continents move. I think you guys are aware that continents move. We're going to be learning about evidence of continental drift. You will get this paper. This is this. It's the exact same stuff that's written here. You will do this activity. You will read, answer those two questions. What? No. Then here is the assignment, and the directions are written here. You will read the evidence on each slide. So these are the slides I'm speaking of. On page 7 for each slide, you will write a short description of the evidence presented on each slide. So basically, you're going to read this slide. You're going to summarize it and draw a quick picture. So you're going to do that for all 1, 2, 3, 4, 5 slides. 1, 2, 3, 4, 5 slides. Then this is the assignment. You will be on a separate sheet of paper. You will be Alfred Wegener. He's the guy who discovered continental drift, by the way. Maisie's familiar with him. You will need to collect evidence. So you did that already. And you are going to write a letter to propose your theory to the other scientists. All it has to be, and it says right here, this letter should include a description of continental drift and a description of the evidence, all 5 pieces. You're going to be convincing the other scientists to believe in continental drift. That letter will be due Tuesday, December, which is crazy to me, December 3rd. So you do have to complete this page and write the letter by Tuesday, December 3rd. This will all be posted on the board, but I just wanted to make sure you had a heads up of what to expect. I'll see you guys on Monday.